Hi everyone, Mr. Lee here. In this video, we're going to go over this concept known as rotational inertia. Now, in this video, we're going to do a lot of really hands-on kind of things. And so whenever I ask you to go get something and really feel the physics, I suggest that you pause the video and actually go forth and try these things. Because one of the hardest things about rotational inertia is if you see the equation, it's well, of course, I understand what the equation means, but to really get the ideas and the concepts behind it, that's where the true understanding happens. I'll also be showing you different simulations, and it's important that when you look at those simulations, that you jot down the notes from those simulations, because those are the big main ideas. Okay, so let's begin. The idea behind inertia. So before we get into inertia, let's focus on the word inertia. Okay, now when we were doing the dynamics unit or the forces unit, we also discussed that Newton's first law is the law of inertia. Okay, and if you remember, the first law states that a object in motion, okay, slash not in motion, okay, object at rest, right, I'm going to just say will retain that motion unless there is a outside force. Unless there is an outside force. Okay, now it's important to keep this law in our minds because that really does help with the understanding of rotational inertia. Now, this entire law can be summarized by this one concept, this one idea, and that idea is the idea of mass. Okay, so we can say that if an object has great mass, okay, it will require a greater force to accelerate. Okay, and that makes sense because according to Newton's second law, net force is equal to mass times acceleration. So if our mass is big, in order to get just a acceleration out of it, it requires a lot of force. And the inverse, of course, is true. If the mass is small, then it will require just a small force to get a amount of acceleration. So this is one of those big ideas. We're building up to this big idea, and this idea here, this is the law of inertia. Okay, so inertia, just think about it like a object's mass, right? Its tendency, well, this is actually what inertia is, the tendency to resist a change in motion. Okay, so this is just a really fancy way of saying that an object in motion will stay in motion and an object at rest will stay at rest. But inertia is that tendency, how likely is it going to stay in motion? How likely will it stay at rest? And the answer to that question of how likely really just comes down to the object's mass. If it has a lot of mass, it's most likely going to resist that motion. If it has a little mass, it's not going to resist that motion. So keep that in mind. All right. So what I want you to do now is I want you to pause the video and I want you to get two different objects, okay? One with a lot of mass and one with a little bit of mass. Okay, so I went ahead and I got two objects. I got a water bottle that is filled with water. Make sure that it's tight. And I got a, I guess, aluminum bottle, okay, no top, but very light. Okay, nothing in there. Okay, so this water bottle has a lot of mass. Therefore, now everyone repeat after me, whatever object you have, hold it. The object with more mass has more inertia. And the reason why I'm asking you to say this out loud is because once you say it over and over again, it kind of just gets embedded in your brain. Okay, kind of like the alphabet, right? Think about how many times you said the alphabet. Now you know the alphabet. And you could probably sing it too. You're probably singing it right now in your head. Now get the object with less mass and say, okay, so the less mass, it has less mass. It's more likely to change. It has less inertia. Less mass, less inertia. There we go. All right. Now, we are doing rotational inertia. Before we do rotational inertia, let's do just the test of a object's inertia. It's regular inertia before we do rotational. Okay, so I have a object here. It is at rest. Okay, follow. In order for this object to move, it requires a lot of force from me compared to this object, which has less mass. It's pretty much easy for me to get it to move. Okay, a lot of mass. A little mass. ha, ha, ha. Okay, and this is the inertia test, believe it or not, and you can do this in space. So the object with more mass, okay, it requires more force. I feel it in my muscles, okay, compared to this one. Freaking easy, man. Okay, easy to change its motion. Okay, so the same idea comes true with a object that is rotating. All right, now look around you. Make sure you don't have anything that you can hit, because we're going to be turning into like semicircles. All right, I'm going to extend out my arm, and I'm going to rotate this. Whew. Okay, now feel it. Now, if you have like a relatively heavy mass, you can really feel it, right? You can really feel that inertia. Okay. Now get that into your body, right? That muscle memory, and do the same with the object with less mass. Extend out your arm and swing. Now I can tell you right now that the one with less mass, this is really easy to rotate compared to the object with more mass, right? Oh man, I really feel it in my hands and my muscles. Okay, so the same idea is true when we did our first inertia test, right? When we were just put it back and forth versus when we were spinning, right? We weren't going full circle. But this is the rotational inertia. Okay. Now put those objects away. Now we're going to get into the notes behind this. So we discussed that inertia is mass-based. Now, because we're doing rotational inertia, not only will it be mass-based, but it will also be radii-based. So let's give you the equation for rotational inertia first. Now I have to do a little caveat here. This is a red star moment. Okay, very important. For different objects, there will be different equations for rotational inertia. Rotational inertia. Okay. This is a very important idea. So what this means is I'm about to show you the equation for rotational inertia, but this is what we call like just this generic equation. This is just a equation that we can use to really understand the concepts of rotational inertia. And what I mean by that, and I'll show you the chart in a little bit, is that rotational inertia for different objects, different shaped objects, there are different equations. But the one thing that really ties all those equations together is this generic formula. All right. The equation, or the generic form of the equation for rotational inertia, well, the variable is capital I, is equal to the mass times the radius squared. Okay, now the radius simply means how far is the object from the center of the spin. Now there's a lot more that's going on with this equation, but what I want to do is I want to show you the different shapes and how those different shapes changes this base equation. Okay, but before we do that, the important thing is that the rotational inertia is based on an object's mass and its radius squared. So before we move forward, as always, let's look at the relationships between the variables. All right, so we have rotational inertia and we have mass. Okay, so if you have, let's say we have like a what's that? I don't know, a ball on a string, right? Like a yo-yo or a ball on a string, and you're swinging it around in a circle. Okay, so this ball has a object M, and it is a radius R away from its, that should be the middle of the swing. Okay, so it's moving around in a circle. So if the ball's mass were to increase, right? So let's say if we were to replace a ping pong ball with, I don't know, like a bowling ball, and we're like swinging it around, the rotational inertia will increase. So this is a directly proportional relationship. Okay, so what does that mean? So if the mass were to increase, the rotational inertia were to increase. So it's very important to know how to put these things into sentences. So what this means is it will be harder to stop moving in a circle. Okay, and this is an important part, it is harder to get the object moving in a circle. All right, so this is what it means if your inertia increases. And the vice versa is true if a object's inertia were to decrease. Okay, so if it were to decrease, you know what? I'm going to write it out because this is important. It is easier to stop the object from moving in a circle, and it is easier to get the object moving in a circle. All right? Or I'm saying moving in a circle, but I mean really it's rotating. Okay, so and this is if your inertia goes down. So let's use my analogy of the ping pong ball and the bowling ball, right? If you were to put a bowling ball on the end of a string and like whirling around in the very beginning, it's going to be really hard to get the object to spin in a circle. If you were to have that object or that string be attached to a ping pong ball, man, really easy to get to whirl it around. Okay, all right, so you have these two objects spinning around, and you need to stop it. How are we going to stop it? Well, you're going to put your hands on it and you're going to like stop it from rotating. The ping pong ball, very easy to stop rotating, right? You could probably swat it out of the air. That bowling ball, if he's trying to swat that bowling ball in the air, I don't know, you're going to have like a broken hand. And the bowling ball is most likely going to keep on spinning in a circle. So that's the big idea here. And you'll notice I'm not really focusing on just the equation, but what the equation means, because that is very fundamental to the understanding of this entire unit. Once you understand the equations, the rest of the concepts kind of flows naturally. Okay, so we have that, and the other relationship is I'll scoosh this one over, is the relationship between inertia and radii, okay, or the radius. So what this means, so if we were to take a look at the equation, if it's just the radius, it will be a directly square proportion. Okay, and we can say that is square because that r, and it doesn't look like just an r, right? In there, it's an r squared, but we're not looking at r squared, we're just looking at r, so it'll be directly square compared to r squared. This will just be a directly proportional. Okay, so this one is a directly square proportional, and this is just a directly proportional. So like understanding that is the important part here. So what does this mean? So let's say if we were to get a object, right? Well, you know what? I'm going to use my two objects that I have. So I have this water bottle, okay, and I'm gonna extend out my arm. So it's kind of easy, right? It's just like a water bottle, like, so you gotta have to really imagine if this were like a tiny bit heavier, right? You can really feel the effects if the mass is big. All right, so extend out my arm, I'm swinging it. Okay, so I'm like, okay, so it feels like this difficult to swing it around. All right, back and forth, back and forth. Now compare that to if my arm's out right here. This is really easy. Okay, this is really easy compared to if my arm's out there. So that's where the idea comes from. So if the radii, right, if the radii were to increase, the object, so I'm going to write this out, you should too, will be harder to start to spin. Man, that sentence is ugly. So is my handwriting. And it'll be harder to stop spinning. Okay. Spinning. And the inverse is true. If the radius is smaller, object will be easier to start spinning. And it will be easier to stop spinning. Okay. Now notice I'm not really talking about like the numerical values of inertia because I'm going to focus on the concepts here. So if the r increases, that means the I increases. If the I increases, what does that mean for us? It has a lot of inertia. It's going to resist motion. Okay, and the inverse is true. Okay, so now that we went over the equations, I just want to do a quick little a showcase of the different rotational inertia things. Okay, and the reason why I want to do that is you don't need to know the following examples or equations because realistically this is the only equation that you actually need. But the types of problems that you'll see different rotating objects. Okay, so I'm going to try my best to draw some 3D objects. So let's say we have a rod. Okay, so we have a rod. Ooh, okay, and then we have, like, right in the middle of the rod, this is what we call the axis of rotation. Axis of rotation. Okay. So what does this mean? So, like, let's say if you have a pen or a pencil, okay, and if you were to hold that pen or pencil, like, right in the middle, and you were to do this, that's what you're doing. Okay, you're measuring the rotational inertia of this motion right here. So if you have that motion, your equation, okay, remember it's always going to be mr squared base. So the equation becomes 1/2 or 1/12 mr squared. So this number right there, that's just describing the object, and the r will be, of course. So you're looking at this right there. That's the radii. Okay. All right. And so if that's the radii, what you're actually looking at is I'm gonna zoom in on this area right there. Okay, zoom in, drawing. All right, so if we're looking at this, the tip of, let's say we'll just call this a pen, right? We're looking at that part. So that means this M is only focused on, so if this were like the end of the rod, we're only focused on this mass right there. Okay, where if I were to continue this bracket, right? So this is like boom, like this is my R. Okay, so I'm like really zoomed in on that image. So if you could imagine, this is the bracket that I drew up there. Okay, now if we were to go lower, okay, so if we were to focus on this area right there, if we were to focus on that area, my radius would decrease. Okay, because here my radius would be like there. But by mass, assuming that the object is all made out of the same material and it's the same uniform mass, my mass would be the same. Okay, so what does this mean for us? This means that out here, all the way out there, because the radius is bigger, that part of the stick is harder to move / stop, okay, because it has such a big radii. Compared to this part of the stick, that part of the stick, it is, because it has a lower inertia, okay, it is easier to move / stop. All right. Now, so that's a stick, and one of the most common things that you'll see, looking at my notes here, will be, I want to show you a difference here. This one's cool. So if we have a ring, okay, so we have a ring. Oh gosh, that's ugly, isn't it? Okay, so we have a ring, and I'm going to draw this as a 3D ring. Oh gosh. Oh boy, this was a big mistake. Oh my gosh, this is so hard. Oh no, digital drawings. All right, that's my ring. Oh my gosh, I'm just erasing that. Okay, so imagine that this is like a 3D ring. Well, you know what I could do? Here we go. Erase. Oh gosh. Okay, so I'm gonna do a 3D ring. Yeah, there we go. Fix it for me. Oh, it didn't fix it for me. There we go. Okay, so we have this 3D ring. Now, if this 3D ring were to be rotating about its center, so that's the center, like this. Okay, so I'll get an object to really demonstrate this. Hold on one second. All right, so I found the ring. Let's see. Okay, so this is the ring. And what I mean by rotating about the center is it's rotating like this. Okay, this is the rotation, right? Compared to like a rotation like this. That's a different kind of rotation. So we're focusing on a rotation that looks like this. All right, so if we were to rotate the ring in that fashion, the equation would be I is equal to mr squared. Now, if we were to rotate in the other way, and I'll show you again. Let's see. Fix it. Oh, didn't fix it. Okay. There we go. Okay, so if we were to have a ring like that, but we were to rotate it the other way, so that's about its vertical axis. So that kind of motion will be spinning around like this. Okay, so the idea is that the axis of rotation, that part doesn't move. It's rotating around that axis. So this is the second one I drew. This is the first one I drew. Okay, so the axis of rotation is through the ring, so it's rotating around that part. And the second one I drew, the axis of rotation is where my fingers are, and it's rotating around that part. That equation would be is equal to 1/2 mr squared. All right, now this is a type of problem you might see. So you have two objects, right? We have one ring, and if I were to ask you, which way is it easier to rotate that ring, right? So if I have a ring in my hand like a hula hoop, right? We could do this with a hula hoop. Is it easier to rotate the ring in this fashion, or is it easier to rotate the ring in this fashion, right? If I was a little bit more flexible. And the way to really look at this is to take a look at the equation. So in here, yeah, the equations look almost identical, except for there's a 1/2 here, and the objects are identical for the situation. And so we can see that this object, we'll call this A and B, right? So when it's about, this is the center rotation, and this is the, I don't know, what's this called, the vertical? This is the vertical axis, okay? This is the center axis, and this is the vertical axis. Because this is 1/2 mr squared, this has half of the inertia compared to this, okay, which has the full amount. So we can say that B is easier to rotate. In fact, it is, I would say like 1/2 times easier, because it has 1/2 of the inertia. All right. Okay, so the very last thing, I know this is a little bit, a longer video, but I do want to show you this, is the final concept of this mr squared, all right? And so if we were to have a object and it's a disk, okay, so this is a solid disk, and to show you that it's a solid disk, I'm going to color it in a little bit. Okay, color in the solid disk. All right, and the middle part is right there. So the equation for this, well, we'll just use I equals mr squared. Okay, we'll just use that basic idea. Is when you are taking a look at this m, okay, you're not looking at the mass of the disk as a whole. Okay, you're only looking at the mass at a very specific radii away. So what does this mean? So let's say we had a disk. So this is like the top-down profile, but let's do a, let's do a side profile. Okay. So side profile, the disk kind of looks like this. Ooh, yeah. No, don't fix it for me. Yeah, kind of like this. All right, so if we were to take a look at this, oh my gosh, I should have did that a little bit better. There we go. All right, so this is the disk, right? And it's a blue disk, so I'm gonna color it in blue. So this is the top down, and this is the side. Okay, so if we were to take a look at this, we can see that the mass is not distributed evenly. In fact, the further away you are, there's more mass. Compared to closer to the center, there's less mass. So this m, what we're looking at is a very specific radii away. So if I were to take a look at this chunk, that chunk right there, so that's kind of like right here, right? We would say that there's more mass. There's more mass here compared to if we were to take a look here, where there's less mass, right? There's not that much. So we would say, so when we're using this equation, we're looking at a very specific radii, okay, and what the mass is at that location. And I know I'm using like a point specific, but because it's radii, it could be there, it could be here, it could be here, it could be here. But all four of these points, they have the same radii. So at those points, it would have the same rotational inertia. Okay. All right. So let's do a quick recap. For this entire unit, it's very important that you really understand what's happening, because in the previous units, when objects move in a straight line, like, it's very easy to conceptualize. But when objects are moving in a circle, it just looks like it's spinning. So it's a little bit more difficult. Get used to the concepts behind it, because we're pretty good at this point in looking at an equation and trying to figure out the relationship between things. Okay, so that's this video for this one. I will see you next time. Bye-bye.